So thanks for being here. This is now the second half of the course. I'll finish off a bit with monad algebras, where we didn't quite finish on Saturday. And I'll talk a tiny bit about monad maps, but then we will go to a different topic, which is co-monads. This is something we will need to model environments. And then the aim of the whole game is to put the two together, which will happen tomorrow, Tuesday, when we will talk about interaction laws, which is then about how effectful computations and environments that they could be put to talk to can work together to achieve the return value for the computation and the final state of the environment collaboratively. Okay, so what was the main thing I tried to convey on Saturday was that we have these monad algebras, also known as Eilenberg-Moore algebras, and they have a very definite programmatic meaning or meaning for programming languages, which is these are deep handlers of effectful computations in the original sense of Plotkin and Pretnar when they introduced handlers. Variations have been introduced afterward, and you can talk about shallow handlers for free monads, but here we talk about deep handlers. So let me recap a bit and then reach the final slides, which I didn't manage to cover on Saturday, and then we move on from there. So what was the idea? The idea was that the monad algebra is a fixed object. No polymorphisms here, no polymorphism here. A fixed object, x, together with a map tx to x. And what was the intuition? The intuition was an algebra of a monad with carrier x is a handler of computation of values of the type x, and only of that type. There is no polymorphism. I really cannot emphasize this many times enough. X here is a fixed object. So this algebra structure map, Tx to X, then you should understand as something that extracts a single value out of a computation of values. So if T of X is a stateful computation, so here we have a function from S to S times X, then somehow from there we have to extract a single value, maybe by providing an initial state or so, for example. A prototypical example is non-determinism. So think, for example, T of X is non-empty list over X for binary non-determinism in this extensional way where we forget about little binary choices. In the end, we have a flat list of elements of X. If I want to extract a single X, this doesn't work for a general type X, but for specific ones, I could have associative operations for doing this. So for example, we talked about maximum for integers or natural numbers, or conjunction or disjunction for Booleans, for example. Right. And I said this has to come with certain quality criteria. These are these two diagrams here. The first one said, if your computation is actually a value just bureaucratically seen as a trivial computation, then you shouldn't have any choice about what the handler can do. The handler has to give you back the value that you started with. And the other one is a sort of a compositionality type of quality requirement or quality criterion, which says, if you've got a computation of computations, there is two ways that you could reach a single value. One is a sequence. So you get one single computation, apply the handler to it. So for example, think list of lists, list, then apply your handler to it in a specific way, extract a summary of the list, so to say. Or you could go in stages, deal first with a second computation or the inner list here. And then you already only have the outer computation left with some values given, which are the aggregates from the second computations. handle this outer computation, crunch it down to a single value. So we discussed this, and I told you about a few examples. I also told you that algebras give you a second canonical resolution of every monad that is called the Eilenberg-Moore resolution, which is the category of algebras. Through that, any monad factorizes with an adjunction. I mentioned in particular, for example, that the state monads have this type of algebras that are called mnemoids. So what was the story here? The state monad is this thing. If you just work from the definition, an algebra is an object X. So that's the type for which we can handle computations of values of that type, crunch them into single values. So here, I give it the mnemonic name, I call it getPut, has to have this type. And if you just write out the two equations I showed on the first slide, they amount to this. This is a bit unwieldy. It turns out that you can break this into two in such a way that you don't lose any information. In fact, you have exactly the same information, just packaged or presented to you slightly differently. And that's what Paul-André Méliès has called a mnemoid. So it's an object X, the same one as here, but then with two maps, get and put, satisfying certain laws. Some people know of lenses. They also talk about get and put that satisfy certain laws. Those are coalgebras of co-state comonads, and we'll get to them today, actually, but these are different, and the types are different. I'm just using the same names. And there is a connection, actually, between the two, which exactly has to do with this sort of computation and environment dual roles, if you wish. So intuitively, if you take X, as X, you take T of X for some X, any X, then get takes you from S arrows TX to TX, and it's just taking a dependency of a bunch of computations on states to a single computation. You should understand it as prefixing your computations by a read based on whose result you decide how to continue, and you get a single computation. And put is similar. You're given one computation TX. You prefix it with writing S to the memory intuitively, and this gives you a new computation then of type T of X. These are the equations. This much, this is what I got. I didn't reach this slide. So remember, I told you of these free functor algebras monads, also known as free monads, although I haven't justified the word free monad here yet. So those were leaf trees. So given any functor f, I could look for any object x for f branching trees labeled with values from x. And this is a very general way of modeling notions of effect in a fine-grained way where you keep track of little actions your computations do. Remember, one of these examples was f of x is x times x. Then when you look at this free functor algebras monads, it is exactly binary branching leaf trees. Yeah. Now it turns out that for this type of monads, the category of algebras of the monad, so the Eilenberg-Moore category, capital Alg F star. F star is this free functor algebras monad, is actually isomorphic to the category now Alg with small a of algebras of the functor. So this is a special case where we've got a functor related to a monad in a certain way. So there is the functor f, there is a monad f star given by free algebras of f, free functor algebras of f. And now it turns out that the monad algebras are, or the category of monad algebras is isomorphic to the category of functor algebras, and not just that, but in a carrier preserving way, or in a way that commutes with these forgetful functors. So a free monad R is a functor and a monad. Well, any monad is a functor, yes. Not sure what you mean. We didn't define functor algebras, but I informally showed you that these are the monads given by these mu expressions. Maybe I should, for a moment, go back to this place. So remember this slide. I told you about the following thing. So, and I informally hand-waved around initial algebras or least fixed point objects, right? So given a functor, I define this monad T, and given X, given an object X, T of X is this object, and that is actually, categorically speaking, the carrier of the free algebra of F. But if you don't know what that is, it's really not important. Just only I will use the terminology here. The important thing is these are F branching trees with X labeled leaves. And we looked at basically two examples. So one is if F of X is just X times X, then of course, you know, this equation here instantiates to this thing because F of Z is Z times Z. And now if you read what this is, these are binary leaf labeled trees because an element of T of X is a choice of either an element of X, more intuitively think, you are in the leaf case then, and the leaf label is an element of capital X. Or you're not a leaf, you're an internal node or a branching node. And then what you have is recursively T of X and T of X. When I write mu Z, it means I'm looking for a least solution of a certain type of equation. Here, the equation is this. So therefore, for Z, you can read Tx. So this was for a notion of non-deterministic computation that I emphasized is very intentional. Remember, we can use non-empty lists for binary non-determinism, where we want to forget about individual little binary decisions. Or maybe you want to use also possibly empty list if you allow nullary choice, but let's just think binary choice. Binary, not nullary binary. So this is a very intentional way of talking about non-determinism. And then we also had another example. So if f of x, you take s arrows x plus s times x, so it's a choice between these two things, then you get these trees. So the free functor algebra monad you do get is T of X is a choice between three things. Either you're in the left, in the middle, or on the right. Or yeah, there are two cases on the right. I call this one middle, and this is the proper right. So the first case is, again, I'm at a leaf. The leaf is labeled with an element of X. The second case is a particular type of branching node where you've got S many children, and at any child node, then there is recursively a tree again. So this corresponds to a little read action. So the computation reads from the memory and then branches according to what came back. The final choice is different. So here there were S many children. Here there is exactly one child. So there is one tree recursively again, but it is labeled with an element of S. So this corresponds to no branching. We write the state, or the computation writes the state, tells the environment the state, and we haven't yet talked about how the environments work, but imagine there is the environment on the other side, and then carries on as the computation. So this is a particular type of trees, which then is different from this one, right? Here you were always binary. Here actually you are, your branching factor is S many elements plus one, right? So S many for all the possible outcomes should you want to read, plus one extra outcome for the case should you want to write. So S many plus one. And this is not a standard state monad, but it's an approximation of the state monad, or an intentional version of the state monad. Yeah, it's an approximation in the sense that it's coarser. Or finer, depending on how you want to look at this. So I'm really uneasy about the choice of the words here. in Haskell, you cannot take quotients, right? So, right, you cannot identify multiple trees, or you cannot. I mean, we discussed this. So, I mean, you can represent lists very well, but it's much more difficult to have meaningful representations of multisets or subsets, right? So, in the case of multisets, the order in a list shouldn't matter, but this is something you cannot express in Haskell on the level of type. So, it would be sort of your invariant about which you have to be honest and frank, but Haskell won't check you. And with sets is even worse because you also have to deal with order. But then with the state is the same. So abstractly, a stateful computation, what only matters is what it initially reads and what it finally writes, because every other little read or write action that happens inside a stateful computation doesn't matter at the end of the day, so to say. But if you want to look closer into a stateful computation, more operationally, if you wish, then perhaps this is what you see. I mean, there is this branching behavior. Eventually, you hope every path will terminate. Non-termination is a separate issue. Here we assume finite trees. So at the end of every path, you have a return value, but then on the way, you do these little read and write actions, and depending on the outcomes, you branch, right? So the ordinary extensional state monad is a quotient of this one. And if you study my Haskell code, you actually see a bit of how you could possibly normalize these trees also to sort of reflect this idea. We cannot take quotients in Haskell, but we could work with normal forms in equivalence classes. Okay, this is where we were, but I wanted to actually talk about these algebras. And the slide on which I am is this. So, so there is an isomorphism between the algebras of a monad and algebras of a functor. Algebras of a monad and algebras of a functor are very similar things. In both cases, with the carrier and the structure map. But for algebras of a monad, there are these two equations, the two quality criteria. For a functor, there is nothing. So now what turns out is these algebras of the monad that by definition have to meet the quality criteria, they actually reduce to something that is simpler, namely the algebras of the inducing functor. Let me explain this on an example. So let's go back to this intentional non-determinism, right? So what did we have here? So we start with this functor f of x is x times x. An algebra here for such a functor is just a map from f of x to x, so x times x to x. So literally just a binary operation on x. Some people call a set with a binary operation a magma, so that's a possible word for this. But just think an object or a set with a binary operation subject to no conditions. So that's what algebras of the inducing functor are. But the algebras of the monad that this functor generates, by definition, have to be these things. They have to be stuff. They have to be functions that crunch binary trees with leaves labeled from x into a single element of x, but subject to two equations. And it turns out these equations basically tell you that you don't have a lot of choice here. You're basically only allowed to recurse over the tree. So what really matters and what you have to know is the recursive case. And that is basically, you know, if I already know what happens so I'm a tree. If I already know what happens to my two immediate subtrees after the crunching, so I've got two single values. If I know from how to turn these two single values into one value, or how to turn the pair of single values into one value, then I know how to turn the whole tree into a single value. Yeah, this is just recursion. This is just folding over a binary tree, really nothing else. But also the opposite. So it's clear that any binary operation like this, sort of any base data for your fold or reduce, if you wish, gives you this function on trees that takes trees to single elements. But you can also go in the opposite direction. So the only allowed functions from trees to single elements are actually those induced by just maps like this. And that follows from the fact that these functions are not allowed to be arbitrary. These are algebras of a monad, so they're subject to these conditions. So remember, for example, that one of our quality criteria says that if my value is a trivial computation, which here corresponds to the leaf case, I have no choice. So one of the arguments to my fold, like the base case, is fixed. If I'm here on the left, I'm not allowed to do anything else than to just return the leaf label I already have there. So literally, I can only do anything for the branching nodes case. And there it turns out that I'm not allowed sort of to do any complicated recursion. I literally can just fold. So that's one example. Yes, somebody already gets to the state monad, which actually wants to be my next example. So let's think about state. So there is two versions of state as well. So we have this intentional state monad that you get like this. So you take a functor f, which here in this case is f of x is s arrows x, corresponding to the reading case, plus, which is another thing a computation may choose to do, s times x, corresponding to the writing case. Now the algebras of the free monad, free functor algebras monad here are maps that take you from this kind of trees to single elements subject to two equations. But as I told you, actually, these functions are not allowed to have a lot of freedom. So literally, you should be able to deal with a step case again. All you can do is to choose a step case because this thing can only be a fold. So literally, what we get is maps from, on one hand, s arrows x to x, and on the other hand, also x times x to x. So it's officially maps from s arrows x plus s times x to x, but of course we can break these into a pair of maps, which you could call get and put. And these are subject to no conditions. So you could call these things premnemoids. But then remember, algebras of the ordinary extensional state monad, a word is missing here, were the same thing. So a set X together with two operations, but there the operations had to satisfy certain certain equations, right? So let me just fix the typo here so I don't forget. Okay, so these are two entirely different monads, right? So the free monad here is the free monad on this F. Yeah, so here is actually Tx is this. So that's the intentional state monad that keeps track of every little step you do. Every step that a computation makes is either to return, so that's how you get out of the computation, or read or write. The extensional state monad says, well, we can't see very deep into a stateful computation, but it's something that where what comes back depends on some state. So that's the basically corresponding to the first read of a computation in here. If this guy doesn't read at all, it's kind of it will be a useless read. You read, but then you don't look at the result. And then it's the final write that also matters, and the rest doesn't. Maybe I should show you the Haskell code for this thing to illustrate a bit of what is happening here. Nick Mulliners asks, if you define the algebraic effect for stateful computations using the free intentional state monad, are the algebraic operations exactly the three? I don't understand this question. So actually in the intentional case, there are no equations at all. So get and put are completely unconstrained. So these extra equations that you, for example, have in mnemoids or for the extensional state monad, those are something that you, as a designer of these monads, have to make up. So in the case of state, for example, you have to say certain stateful computations are identified, and you start saying things like reading and deciding based on the read result, and then reading again and deciding based on the read result. Is the same as just reading once, because there is no point reading twice in a row. You're guaranteed to get the same result. And these kind of considerations tell you what kind of sort of extensional computations you'd like to consider to be indistinguishable, because the difference is so small as to not matter for you. So let me reshare, and then I can show you the difference between the two things. Okay. You should now see two windows, I hope. So let me show you two forms of state. So this one, if you're a Haskell programmer, you surely know. This is the usual sort of extensional state monad. So the monad applied to X is S arrows S times X. And the free algebra of this monad state S on X is actually has as the carrier this function space S arrow S times X, which is what state Sx is. Let me try to make it so I don't need to scroll here. Opa. Yes, so that's what state Sx is. I forget about these bureaucratic data constructors. So you can break the mult down into two parts in this particular case, and we can put a general one for free noise. These define them for state. This prefix. Is how we prefix a computation with a right.
Can you restate what you just said for like the last 3 sentences, because it was unintelligible?
Oh, did something happen to the audio? Okay, I'll state it again. Is it better now?
Yeah, it came back now.
Yeah, maybe it was just completely accidental. So I said this was the standard extensional state monad, where you sort of see a very abstract version of the state, right? So I mean, the final return value only depends on the initial state, and also the final state is produced. Everything else that happens in between is invisible. And then I said the free algebras of the state monad on any given object is just the object is S arrows S times X, and the structure map is mult. This is a generality, but then we can decompose mult into get and put, as I told before. And then I said get and put for the case of free algebras of free mnemoids corresponds to sort of prefixing a computation with either reading or writing. So this happens if you've got the dependence of a whole bunch of stateful computations on S. We can use it to encode prefixing by reading. So the resulting computation is what? Lambda S, and what we give back is we use this function here, f, which is this guy, at S. But then also we have to apply it one more time to S to actually be here. So this corresponds to then choosing actually the correct continuation or computation among the many ones given. And in the case of put, what happens? So here is a thing we want to write into the state. So we write the data value for the state. Here's computation.
It's breaking up again.
And how I do it is we produce this computation that reads, sort of bureaucratically discards the result altogether, but just continues as this one would be on S. So this is sort of we simulate putting. But the intentional version of the state monad is different. So it's this, it's these trees, right? So here I haven't written it as an instance of the general free monad. I mean, the code is somewhere below in the file, but the special case of these leaf trees. So red X corresponds to returning, then there is something for reading, then there is something for writing. And this is how the monad structure, the free monad structure is defined on this one, which basically just goes by substituting trees into trees. So the only interesting case is the red case. So if you return, but if you don't return a value, but the computation again, then you say, okay, this is the final flat computation that you do get. And in the other cases, you just work homomorphically. But then, so here it looks like these trees could be arbitrarily deep. Yeah, you can do an arbitrary many, you can do arbitrary many, you can apply arbitrarily many get and put actions after each other, and then maybe at the end of the day only to return. Whereas morally, you should be able always to reduce this to just only getting at the beginning and putting at the end. And you could implement a normalization function for these type of trees that actually will compress any tree like this to a tree of depth 2 or 3, depending on how you count. So it would be first getting, then putting, then returning. And there is 2 ways to do this. One is to convert from from state back to I state, because any extensional stateful computation clearly is just get followed by put followed by return. Whereas in this direction, you actually have to use the equations that hold for the intensional state monad, for the extensional state monad, sort of on the fly, to do some rewriting and to produce from an extensional stateful computation an intensional stateful computation. Right, but that's yeah, you should study the code. I can't go deeper into it, but I'll be very happy to comment it in Slack. But the important point is there is this correspondence between intensional versus extensional modeling of notions of computation. The intensional ones are very systematic. These are just these trees, leaf trees, where at branching nodes you have your elementary actions that you want to think of as your effectful actions. The more extensional ones, there you decide how much you want to hide, right? I mean, non-determinism is a particularly good case because you start out with binary leaf trees, but then you say, maybe I want to identify them up to associativity, which boils down these leaf trees to lists, because every tree by sort of applying rotations can be turned into a right-leaning, fully right-leaning tree, which is just a non-empty list. And then you could further quotient, say, by multiplicity, which takes you to So which is the idempotence equation, which takes you to multisets or bags. And then finally also by commutativity, which takes you to then power set. So you model non-determinism simply as sets of values. These equations by which you want to identify computational computations. This is hard. It really depends on what you want to do. The sort of a deeper story here is the one of algebraic operations into which I have no time to go into at all.
Can you repeat the first part of this section, because you were breaking up a bit?
I can. Let me also stop the video just in case. Why is this happening to us again? Yes. So what I said was, a big takeaway is you can always model your notions of effectful computation by these free functor algebra monads or free monads, which are these leaf trees for particular branching types, which you specify by functors f. And this is also very convenient for Haskell, because there you can simply code this. I think I also showed it the other day. It's further down here. So in the end, these free functor algebras monads, they are all these leaf tree type given monads, right? And you just instantiate f for a particular thing. So for example, for non-determinism, f of x is x times x or something like this. And for state, as we considered, it is something more complicated. Whereas these more, so that's for intentional notions of computation. But then when you want to abstract, you want to make your computations more opaque to the environment. You want to say, okay, these are my internal details. I don't want to expose these to anyone. This comes, I mean, this leads you to basically quotienting these free functor algebra monads to some more specific monads, and coming up with these equation systems or equational theories is an art. So the prime example here perhaps is non-determinism, where you can think that very many levels, like you think, I could say, non-determinism means non-empty multisets. You could say it means non-empty power set, yeah, non-empty subsets of a given set. It just depends on how much you want to see about what happened inside the computation. Of course, it becomes important for interaction, because if you're very opaque, then it's difficult to have meaningful interaction. But we'll see this tomorrow. I'll quickly tell you about monad maps, and then I go to comonads. So monad maps are to monads like perhaps natural transformations are to functors. Intuitively, for functional programming, they also have a very important meaning. To have a map between two different monads, T and T prime, means you're able to convert between two different notions of computation. Yeah. For example, a typical monad map actually would go from binary leaf trees to non-empty lists, and this corresponds to identifying certain binary leaf trees as amounting to the same non-empty list, right? Which is basically just a frontier of leaves of the tree, read from the left to the right. So what is a map between two monads? It is essentially just a natural transformation between the underlying functors, but again, certain quality criteria has to be satisfied. So certainly, if you convert from Tx, but your element of Tx was just obtained from a single value, viewing it as trivially a computation, then your conversion shouldn't do much. It should actually amount to just viewing X as a trivial computation according to that notion. So this experience says, what is a trivial computation for one notion of computation That one again is a compositionality requirement. So if you've got a computation of computations according to the first notion, you can sequence, get a single computation, you can convert. So maybe like a list of lists, convert it to a single list. Sorry, I wanted to say a binary tree over binary trees, converted to simply a binary tree, then turned into a list, must amount to the same as converting the individual computations, outer and inner ones individually. So suppose you have a tree of trees. I could turn it into a tree of lists, or maybe a list of trees. That's the order in which it's written here. So I first maybe convert the outer computation. So I do get a list of trees, and then I could also turn the inner trees into lists. And then I should be able to use sequencing according to the other notion of computation. I need to get to the same result. Does it make sense? So if you define this notion, then monads and maps with them between them actually form a category. And yeah. So this is, if you love abstraction. So the category of monads on the category of C is actually just a category of monoids in the end of functor category. You have a similar, because you can present monads as Kleisli triples, there is an analogous formulation for Kleisli triples that just works with the Kleisli extension. Not important for the moment. We should rather think about some examples before we go on. So let's think about, for example, how would I convert between two different exceptions monad? So I could work with Tx is E, but maybe T prime X is T prime. So exceptional computations over a set of exceptions E prime. What do you think are my possibilities? Well, officially, I need natural transformations, sending X plus E to X plus E prime, of course, but not arbitrary natural transformations, because these two extra conditions need to be satisfied. So if you think about it a little, then you'll find out something that is quite intuitive. So to have a monad, to know a monad map, all you need to know is what is every exception according to the first notion of exceptional computation converted in the second one. So an impure computation in one notion can only turn into an impure computation in another. So the equations force this, but the question is, how is the conversion done? So somebody tells you how to go from E to E plus E prime. But actually, also you need an element of E prime plus 1. So in the general categories, you would write a map from 1 to E prime plus 1. But instead, just think an element of E prime plus 1. And that corresponds to the following thing. While computations that raise an effect cannot become computations that just return a normal value. That's not possible in this conversion. It's possible that normally returning computations turn into exception raising computations. So here you have a choice, which just basically says for every normal computation, you can choose.
You're lagging, sir. You're breaking. You're breaking. You're breaking, sir.
Let me maybe just share only one window and let me see if this makes things better.
I think you can try to turn off the video. That might help.
But I turned it once. Why is it on again? Oh.
Yeah, I didn't think the first time it was
something
off.
Turned it on. Okay. So now it's only one window. So this is an example of a monad map, for example. And you can also think what it is to convert between two different reader monads, one for a state set S and the other one for a state set S prime. It turns out that a map between two such reader monads is just a map between S and S prime, but in the opposite direction. Here's a funny one. So to go from the state monad for states that S to a state monad to for states at S0, actually you need a lens, or a very well-behaved lens. So what is that? So this is just a pair of maps going between S and S0 in forward and backward directions, almost, not quite. Officially, it's maps with these types. So from S0, I need to get to S, but in the opposite direction, I need to get from S to S0, but I can also use an element of S0, satisfying certain laws. And so one thing that the concept of monad map gives you is that you can actually say that these monads of leaf trees that we defined, they are really free monads in the categorical sense. So I loosely used the word already, and in the Haskell crowd, you always talk about free monads for these monads of leaf trees. But why are they called this? So in category theory, you're not allowed to call anything you want free. Free has a very specific technical meaning. Free literally means left adjoint to forgetful. And here is the adjunction that gives rise to this thing. So if this monad delivering free functor algebras of a functor f exists, it is free in the categorical sense. And that means the following. There is an adjunction between the category of endofunctors and the category of monads on C, where the right adjoint takes a monad and just forgets it's a monad. It just returns the underlying functor. So it forgets about the unit of multiplication. The left adjoint takes an arbitrary functor. An arbitrary functor is not a monad in general, but there is a canonical way of turning any functor into a monad. Well, if the category is sufficiently rich. So here it suffices that these free functor algebras exist, for example. And then this is the left adjoint. So remember, I told you about these natural bijections that are always sort of helpful to keep in mind to remember what is happening in a junction. So here it boils down to the following thing. F star being the free monad on F literally means nothing else than that. For any other monad T, if you've got a map from F star to T, which is a monad map, to have such a thing is the same as to have a natural transformation between F and the underlying functor of T. So above the line here, we're in monads. Below the line here, we are in functors, which means that maps are just natural transformations. So, and here's the last slide about this bit. It turns out that monad maps from an arbitrary monad to a continuation monad are very special. So I told you about this external continuation monad for a given object or set R, which was defined like this. And actually in sets, the external continuation monad is the same as the ordinary continuation monad, but in other categories, there is a difference. Now, the striking thing is that algebras of a given monad, a given arbitrary monad T with carrier R are exactly the same thing as monad maps from T to the continuations monad that uses this object R as the answer object. For those of you that know, here is a kind of a sketch that motivates why this could possibly be true. But of course, checking involves more. You have to check that the equations governing algebras and the equations governing monad maps entail each other here. But the following is true. So to have an algebra of the monad T with carrier R, you certainly need a structure map, which is a map from TR to R. It has to satisfy equations. By Yoneda, this is the same as to for any X. It's the same as to have these family of maps for any X, natural in X, between maps from X to R and maps from TX to R. And then this is the universal property of power that says that these guys are exact the same as these guys, but now this is the type of what a monad map is, because a monad map has to take you from T applied to any R to the external continuations monad applied to any R. Sorry, to any X, naturally in X, right? And this is why the external continuations monad is nice. So you could try to use the ordinary continuation monad and have the same theorem. Yes, Alex Liu said that the second line is the Kleisli-triple-based definition of an algebra. Excellent, that's exactly that. So if we start with the Kleisli-based definition of an algebra, then kind of the, you know, the connection between the two things is one step shorter. So I can, instead of starting from here, going to here, I can start already here. So Alex, this is absolutely great. Then you would perhaps hope that that you could actually achieve the same with the ordinary continuations monad, but you can't. But there is something here that holds for strong monads. So the ordinary continuations monad is strong. And then it turns out that strong monad maps between an arbitrary strong monad and then the ordinary internal continuations monad are again in bijection with algebras of T with carrier R. Okay. People complain about me not showing Haskell anymore. Let me see if I could. I think I wrote here also something like that, but maybe it gets a bit more specific to go into right now. So I certainly have the continuations monad. In Haskell, we can't make any difference between the two anyway. So in Haskell, we are in this unique strength type of situation as in set. But maybe the monad map thing is not written up in this particular file. We could discuss it in Slack if you want. Yeah, maybe on an ideological level, this is maybe one justification for saying why continuations monads are the mothers of all monads. So literally can talk about algebras of any monad in terms of monad maps from that any monad to the continuations monad for the carrier as the answer object. Now guess what? Okay, 2 more slides. Monad maps are actually one reason why they're useful is they allow you to convert between Kleisli categories and between Eilenberg-Moore categories, which should be quite intuitive, because if you can convert between 2 notions of computation, maybe you should also be able to convert between the you know, impure functions according to both notions of computation. And that is actually true. So you can go from Kleisli T to Kleisli T prime if you have a monad map in such a way that this diagram here commutes, which just basically means if you start with a pure map, you view it as impure according to one notion, and then convert. It is just the same as viewing your given map as your given pure map as sort of bureaucratically impure in the other notion. And the definition is actually very simple. So this functor V does nothing on objects. We don't want to change the types or sets or objects. But on maps, what do we do? If I'm given the map from Y to X in Kleisli T, which is just a map from Y to TX in the base category, how do I get to a map from Y to X in the other Kleisli category? Of course, I just post-compose my given impure function with a conversion to the other notion, nothing else. And this is in forward direction. So if the monad map goes from T to T prime, then the other guy goes from Kleisli T to T, Kleisli T prime. Not the same for Eilenberg-Moore categories. So you can also convert between algebras. So you can convert between handlers. So if you can go from T to T prime, then given a handler for computations in T prime, yeah, for a particular type of values, you actually get a handler for computations according to the notion T. for the same type. And that's also kind of easy, right? So what would you do? So given an algebra, which is a handler, according to t prime, so I know how to go from t prime x to x, surely I can precompose it with tau at x, and I have a map from tx to x, so which by the type at least looks like a perfectly good handler for type x in the first notion of computation. But also the quality criteria, they are sort of transferred from the given handler to the new handler we are making. So everything is good. I mean, there is some verification to be made here, but that is true. But you see, this now goes in the opposite direction. So to go from algebras of t prime to algebras of t, you actually need to be able to convert between these corresponding notion of computation in the converse direction. Right. Now, guess what? Comonads. I want to be very short here. Comonads are co-monads. So in some sense, I shouldn't need to tell you anything, right? So maybe we should all just go home. Or if you don't like this, that they are comonads in COP, I could perhaps say that instead of them being monoids in the category random functors, I could tell you that they are comonoids. And it's true. I mean, all of the theory carries over, and I'll flash you through some of it. And I don't plan a lot of time for it. But you should agree with me that actually there is something to say, because the question is, what are now the examples? Or do we even get any meaningful examples at all? Or what is the functional programming meaning of those examples now? And that is the interesting bit here, right? So the theory is absolutely not interesting, at least the basic bits of it. I mean, if you know that finite Two monads are the same as algebraic theories, and then you'd like to somehow carry this over to comonads and ask, what is the right thing to say here? Things get quite interesting and subtle as well, but not on the level that we are dealing with here. Is this okay? So now my plan is actually the same as on Saturday. I'd like to take a 5-minute break and then flash you through the definitions, but the main thing is to show you some of the main examples and how they differ and what their meaning could be for us as programmers. This is maybe a bit less intuitive. It's going to be less intuitive, but hopefully the intuition will get stronger tomorrow when we talk about interaction, because in some sense, you don't want to think about these environments as, you know, kind of things in themselves, as you say in German, but the real significance for us, at least in this story, is that we can model environments with comonads, and then there is the story whereby you run effectful computations when somebody gives you an environment, right? A naked computation doesn't run, but the computation put in confrontation or in friendship, however you call it, with an environment will be able to run following a protocol that we call an interaction law. Okay. So how about the break until 45, and then I'll try to finish by 05. Okay, so I'm back, and I should probably turn off the video immediately. Covered channels, indeed. So this is where we were. What is a comonad? I want to talk you through these two slides, the definition and intuition. So on the level of a definition, a comonad is a very similar thing to a monad, except all the arrows are turned around. That's what duality is in category theory, right? So a comonad is given by a functor. It's always called D. So that plays a similar role to the functor T in the monad case. Then there is a natural transformation called the co-unit, and the Greek letter for it is epsilon. You could also think epsilon for extract. That is not a bad idea. That goes, instead of from identity to T, now goes from D to the identity, right? And then previously we had mu, which went from T after T to T. Now delta, which you could also read duplication rather than extraction, goes from D to D after D. It's called the co-multiplication. And these are the diagrams, which again are the same as the ones we had for a monad, except all the arrows are turned around. Now, before reading these diagrams out for you, I should really give you the intuition that I will use in this course. So for me, like T was a notion of computation, yeah, some idea of computation. D is a notion of environment, environments of some flavor with whose help computation can run. And what is an environment? A computation was a process that did stuff, basically try to talk to the world, and then eventually hopefully return a value. An environment is sort of a complement to it. It's a process that is able and willing to serve computations and is at any moment in some state. And here is a sort of a funny duality to computations. So in the case of computations, we talk about the final return value. There is no value of interest to talk about until the end of the day. An environment at any moment in time of its life is in some state. I should say it's a server type of process. So typically it would be non-terminating, right? So in a typical interaction between a computation and an environment, there are other variations are possible as well. But sort of the prototypical case is the computation steers the interaction and says when it wants to finish, and then the environment is left off there. I mean, it's a server, it could go on, but the computation doesn't want to talk to it anymore. So now what are these Ys and Ds and DDYs in this picture? Like previously we had X, TX, TTX. Y is the set of states or type of states or object of states of an environment. So this can vary, right? Any Y, so it's just a schematic variable for a typical state set. dy would be the set of environments with states of type Y. So T of Y was computations over X, D of Y are environments over Y. So it's environments whose state space is Y. And then finally, D of Y is a funny case. So that's environments that use other environments as their states. So environments which as states use environments with states of type Y. Yeah, this may sound a bit bizarre, but then let's look at the primitives here. Epsilon does what? Given an environment, which is a process that at any stage is in a state, epsilon takes such a thing, such an environment, that just extracts the initial state. So this primitive will be useful for halting the environment before you even get going at the start moment. In the interaction, it will actually is a useful thing to interact with trivial computations that want to return immediately, that don't really want to talk to anyone. Then delta duplication, of course, is something that has something to do with sequencing. So it takes an environment and blows it up into an environment that have environments as states. In what way? So given an environment, it produces a new one which at any point in time has as its state the current remainder of the environment. So this may be a bit abstract, but it becomes more concrete. But it's sort of useful for pausing the environment at any point in time with the intent to resume. And then, therefore, in the states, so you transform an environment into a more complicated environment that actually just consists of remainders of the original environment. This will work well with compositionality. Then maybe let's try to read one or two of these laws against this intuition and see where we get. So let's take this one. I think that's the simplest. So we've got an environment. Remember, it's a stateful process, willing to go on forever, serve the computation, always happy, you know, a truly servant attitude. And then we blow the environment up. So we get a new environment that, as state space, uses environments over Y, and at any given time, actually, what we see there is the remainder of the given process at that point. Now, if we further apply this thing, that we actually take the very first state of this environment over environments, what I get is what the remainder of the environment is initially, which is the full environment, right? So the remainder of a process at the beginning of the process is the whole process, right? Let's read this one. So an environment, again, we blow it up, but then we do a different thing. So here I've got this environment, which at every state, actually, or at every time, I should say, remembers the whole remainder of the given environment at that time. And then at any of these times, I just want to say, I don't care about the whole remainder. I just want to know the initial state at the remainder. And that's the state that was originally there, right? And here there is something more complicated along those same lines, but you could imagine how this works. Maybe I should give you the simplest example right away. So a good comonad is streams. So you could think D of Y is streams over Y. And then epsilon could extract the head of a stream. And delta could blow up a stream into a stream of suffixes of the original stream. And then you could easily verify that what I told you here kind of works. So this is a very simple case where there is no idea of branching in this notion of environment. That is a process. It's a purely sort of deterministic, or sort of, if you depict it graphically, it's a linear thing. It's a sequence of states, more or less. Right. Okay. So you can see these comonads, again, you can define them sort of in a different way. So you could say D perhaps doesn't need to be a functor from the start, epsilon perhaps doesn't need to be natural from the start, and maybe instead of multiplication, sorry, co-multiplication, I could do with an operation on maps indexed by X and Y, all objects, such that any map from dx to y, I can sort of promote into one from dx to dy. Yeah. And you can see that this beefing up here happens in the codomain. Previously, it happened in the domain. So that's called the co-Kleisli co-extension. Right. And as before, functoriality of delta, of D and naturality of epsilon and this co-extension are not required, but they follow. And actually, the two things define the two concepts are equivalent. So it's a matter of taste and also convenience, which one to use. And frequently, you just switch back and forth. So this co-Kleisli format very quickly takes you to the co-Kleisli category of a comonad, where the objects are the same as in the base category, but the map there from X to Y is a map of the base category from dx to Y. In particular, the identity at Y needs to be a map from dy to Y, but we've got one given, namely epsilon at Y. And you can also define composition in this co-Kleisli category from composition in the base category using the help, the kind help of either co-multiplication or co-extension. And then there is a story of the base category being included in the co-Kleisli category. You do get an adjunction between this inclusion and a functor in the opposite direction, that for every that on maps just applies D, sorry, that on object just applies D, and that on maps is just a co-Kleisli extent. Oh, there is still a typo here. That has to be D. An important thing are co-monad co-algebras, and they have a functional programming meaning again. So when algebras of monads were handlers, co-algebras of co-monads, you could think of them as co-handlers. That's an easy name to make. We also talk about them as co-effect producers. So what is it? Of course, formally it just has to be the following thing. It has to be an object, a carrier, together with a structure map, y to dy. So this is some state set or state object that you choose. And then what is this guy? So this, if you wish, could be a dynamics of a machine or something like this. It is some way to assign to every possible initial state a whole environment or a whole process starting at that state. So any way that you can use that meets certain quality criteria for, again, if you wish, blowing up an initial state into a whole process qualifies. And then the quality criteria are kind of natural. Like if you turn an initial state into a process starting from that state, and if you then want to extract the initial state, you better get back to what you got, what you started with. And this one says what? So I can turn a state into an environment, then blow it up. But I could also turn a state into an environment and then blow up the individual states in that environment. And these two must give the same result. So co-algebras form a category because there is also a good notion of map between them. The category is called the co-Eilenberg-Moore category. Don't ask me why it isn't Eilenberg-Moore, but this is life. And I already told you, a co-algebra is a co-effect producer, a co-handler. And then also, similarly to the Kleisli extension, you get a co-Eilenberg-Moore adjunction. And also similarly, any adjunction actually gives you a co-monad. So for monads, we had what? So if you had any adjunction, then going like this gave you a monad on C. So R after L, sorry, L after R. Oh, no, I already turned the picture around. Anyway, so now I wanted to say if you do first L and then R, you get a monad on D. But now the two categories have switched roles. So here I want to say, if you go first R, then L, then you do get a comonad. So from any adjunction like this, if the categories are named this way around, you do get a comonad on C and the monad on D. But here we emphasize the comonad on C. And then resolutions form a category, and the co-Kleisli is the initial, co-Eilenberg-Moore is the final object of the category. Now, finally, some examples: co-reader, co-writer, co-state, and streams, and co-free. Co-reader. So what was the reader monad? The reader monad was Ty is S arrows Y. So the computation wants to read from some place, and then the value depends on the what was read. A co-reader comonad also worked with an object or set of states, but now the arrows has become times. So dy is S times Y, and the idea is we are dealing basically with a process that's happy to help a computation that wants to read. So this process is a simple one that is happy to give the data value from S to a computation that asks, and then finish off in the final state Y. Right. Actually, it doesn't ever change its state, which you can see from this definition here. So extracting the state, if I've got a pair of S and Y, I just want to return the Y. Blowing up, so S times Y is blown up into S times Y. So a state is replaced with the whole environment, which is basically the copy of the initial environment I had, which was the whole thing here. Satisfies the laws. Chutasano asks, is the duality here for all exists and arrow implication and product? Yes and no. It gets far more subtle, but for the start, this is good. For the start, this is good. But it's not quite like this. Okay. It works on the example of co-reader, co-writer, and co-state, but more interesting things happen. And in general, this is not true. But that's an excellent observation. So what is co-writer? In the case of writer monad, the monad wants to write, or actually to log something, right? So remember, the writer monad is not about overwriting. It is just basically about, you know, writing into some unerasable history in general. But of course, you know, in specific cases, you can also lose information if you want. So dy is p arrows y. Extraction. This doesn't work with an arbitrary object. It works with a monoid object. So you need to go from p arrows y to y. Well, what's a canonical way to get out of this function space? I need to apply the function to something. What's the canonical thing to apply the function to if the domain is a monoid, maybe the unit of the monoid, right? So apply. So if epsilon is applied to some environment, I need to apply this environment to O, the unit of the monoid. And here's your multiplication. So p arrows y, I can turn into p arrows y using the monoid operation, like in the case of the reader monad. And then there is the co-state comonad. This was originally called the array comonad. That's the one that turns out to be the universal one. And I will make this precise. What do I now mean by the universal one? For now, it means nothing. Comonad talking to the state monad. So given an object S of states, or a set of states, it is like this. And what Chutta pointed out here, it seems like arrows turns to times, times turns to arrows in some way, right? And maybe some of you know session types, and this might also ring lots of bells to you, right? So what's this? So basically this S time, so this S here corresponds to the computation to be happy to provide the initial state. Sorry, the environment being happy to provide the initial state for the computation. That is the other party we're talking to. And then as the next stage, of course, the computation wants to write back the final state, and the environment will be happy to listen to it. And then depending on this, finish in some state, right? Now, this is an extensional coding, so you do not see all of the little actions that happen, but it's a complicated sort of way of summarizing what the process could be like. So where here is the initial state, you can actually see if you thread through the state. So if you're given an element of S and a map from S to Y, you can get an element of Y by just applying one to the other, which corresponds to, like, you give the state to the computation doesn't do anything to it, gives it back to you, and then you finish off in a final state, which is your initial state actually here in this case, because nothing happened. And delta is defined like this, and I invite you to read it also in the Haskell file actually. So as I told you before, and this is a minor remark, so there are these variations of working with, like, products versus big co-products that are called co-powers, or function spaces versus big products that are called powers. So we could also work like this. So bullet here is stands for a many-time co-product of copies of S, and you take this many copies of S, this set many copies of S. Now these are co-state monads, are some comonads that actually arise easily from some adjunctions that aren't co-Kleisli, that aren't co-Eilenberg more either. the co-state comonad arises from the same adjunction as the state monad, but just by composing the adjoints the other way around. And similarly for the external co-state. So I won't discuss lots of examples of coalgebras for now, but the important ones are maybe for co-state and then for these co-free functor coalgebra delivering comonads that I'll also get to, which are the same as co-free comonads. So coalgebras of co-state comonad are interesting. By definition, what is there is there is an object, a carrier y, together with a map from y to d of y, which in this case is this guy, subject to two equations, my two quality criteria, one having to do with doing nothing, the other one with sequencing. Now, again, these equations are a bit unwieldy, and it's clear that here we could actually talk about two maps, because, I mean, a map into a pair is just two maps. We could separate them out, call them coget and cobut. And the two equations then become, they rewrite into three. And those are actually the equations of very well-behaved lenses from bidirectional computations. And I'm not calling the operations here get and put, because I already called those for the state monad algebras get and put. But they are clearly related, and in actual interaction, these gets and co-gets and puts and co-puts, they are the ones that work together. Okay, finally then, so what is this most generic notion of environment? Similarly, I mean, we know that these very general intentional notions of computation, they are leaf trees for various branching types, well-founded leaf trees, I should say. You know, every path is finite. So here there is a dual story. We have this comonad for any functor G, well, assuming the category has enough structure, that we here call G daga, which delivers co-free, and this should be coalgebras of a given functor G. What are they? So dy is defined as the greatest solution in W of this equation. W equals y times GW. So if you spell it out, sort of maybe more easy to read, I'm after an iso recursive solution, or I'm after an iso solution for this recursive type equation. dy should be isomorphic to y times g dy, and in a technical sense to be the greatest solution, final coalgebra, if you wish. What are they? They are trees again, but not well-founded, but non-well-founded. So it's okay if paths are infinite. Branching again is determined by G, the given functor. But then here I have times, not plus, which means it's not that every tree is a choice of there being a leaf with a label and then some children that root subtrees, but there is both a label and children rooting some subtrees, and there is no special leaf case. I mean, G might contain leaf case in it, but here what do I have is non-well-founded G branching trees that have branching nodes labeled. Yeah, and in general, there don't even need to be any leaves. I mean, it's perfectly okay if G doesn't contain any plus, so there is no termination option even. So what are epsilon and delta? Epsilon extracts the label of the root node. The root node is a branching node, extracts the label. It's like the beginning of the process. And delta, it blows a tree into trees where every node label is replaced with a subtree rooted by that node. So that perfectly matches the intuition I gave you at the beginning. Remember what I said? There was this idea that the environment is a process. Now the process is depicted as a tree, sort of, you know, the time progresses from you start at the root and then you walk down some path guided by something. Maybe the computation helps you to choose which way to go down the tree. And then every node of the tree is relabeled by the subtree rooted by that node. This corresponds to every state being replaced with the remainder of the whole process at that point in time. Okay. So let's look at some examples. So if gy is y, then the comonad is the least solution of the equation dy equals y times dy. So these are just streams. So this is unary branching, no real branching, right? And also no termination option, just an infinitely ongoing stream of little y's from capital Y. If you take gy is 1 plus y, you get dy is the least solution in W of the equation W equals y times 1 plus W. So these are non-empty co-list. At any point, you can see an element of y, and then either the thing finishes or you see more stuff, which again is an element or finishes or an element or finishes. So these are co-lists. By co-list, I mean possibly infinite lists, but non-empty. There at least has to be a first element. And if you think about sort of what does this relabeling a tree, replacing every node with a subtree rooted by that node means in these special cases, it's of course just suffixes of streams or suffixes of non-empty co-lists. And here I think is the final. Yeah, there is exactly 2 slides to go. So this is the another example, a more complicated example of the sort. So if we take gy, this functor that generates for us an equation for which we will look for the greatest fixed point. If this gy, if this g applied to y is s times y times s arrows y, we do get a type of node labeled trees. Yeah, what are these trees? dy is the following thing. At every node, I have the following things. So there is the node label y. There is, and you see there, it's all times here. There is no plus. There is a data value, so an element of S that I'm willing to give the computation if the state wants to read. And this W is, of course, recursively dy. Yeah. So then you continue. So there is the continuation for the case when the computation wanted to read. But then also, the computation may want to write, and then I have to be prepared to anything that it may want to write. So I'm happy to listen. So it's a function space. So for any data value, for any anything the computation may want to overwrite the state with, I will have here, you know, a residual environment or the continuation environment, so to say, how the process continues. So that's an intentional version of the co-state comonad. So previously we had 2 versions of the state monad. Now we have 2 versions of the co-state monad. In the monad story, the extensional one was a quotient of the intensional one. Here, the extensional one is not a quotient. It's a subcomonad. So not all trees here are meaningful. Not all of them follow the normal contract of a faithful server to, you know, toward the computation that that acts in good faith. Because it's possible here that I choose when the computation wants to read, I provide it the value and I continue in some way. And then the next time it wants to read, I give it a different value and then continue in some way. So there is lots of ways in which you can cheat in these general trees. But then there are well-behaving trees that follow the contract. And these kind of trees, actually, you can normalize down to this thing. So well-behaved or like good trees, I should say, they actually correspond to this one. So this is a subcomonad obtained by keeping only these environments that faithfully implement what should normally be called state. If you take this one in general, this is like a completely unfaithful guy. It It will give you arbitrary values in general when you want to read from it, and when the guy writes, you listen, but then you continue arbitrarily, and next time you don't necessarily give back the same value if the guy wants to read. So it's just like an adversarial, generally an adversarial co-state. Okay. You get something nice again. So coalgebras of co-free functor coalgebras comonads, they are actually the same as coalgebras of the inducing functor. And this isomorphism is identity on carriers. So for example, officially a coalgebra of the stream comonad is an object Y with a map from Y to stream Y subject to two equations. So from a given Y, somehow a stream of Ys is produced. But actually, any one of those that meets the two equations can more simply be described as a map psi that just goes from Y to Y. So the idea is, given Y, this will be the initial element of your stream. There is no choice there. This Y that is produced by psi is the second element of the stream. And then this function, Y to Y, actually, given any stream element, produces the next stream element. So is a little state machine, actually, that generates the whole stream. Yeah? And nothing is observed. So it's just a thing that from one internal state gives you another. So that's what you get here. And similarly for this co-free functor coalgebras comonad in the case of this functor that we had. So coalgebras of the extensional state monad are co-get and co-put subject to the lens equations. But if you work with this intensional state comonad, coalgebras will be pairs of maps co-get and co-put. I put co-get prime here because the type is slightly different, subject to no equations whatsoever. So this means you can behave in a completely unlawful way. I mean, nothing in this intensional co-state comonad checks you on this. That's, now I ran seriously over time, but that's all I wanted to say here. This will become quite a bit more concrete tomorrow when we finally put this machinery together. But before tomorrow, I invite you to recheck the slides and check the comonad code so that you understand how these node level trees work. If you wonder why it's co-get prime here and co-get here, it's kind of a story of an extra equation, because from this generality, you get a map from the type with the type Y to S times Y. But of course, you can impose an equation that says that the second component of a pair returned by co-get prime equals the input. And that will basically render the second component useless because it's predetermined always. And that is morally what is happening in this extensional co-state comonad. So you could say it has these two things subject to three of the lens equations, but you could also say it's these things subject to actually four equations. One of them being this one that says this bit here is useless. It basically says when you get, state should never change. Intuitively, okay, I'll answer a question then still. I'm done with the lecture. Alex, you asked, intuitively, how should we think about the difference between a handler, algebra of a monad, and an environment, which then is an element of the comonad applied to some object? They both seem to be trying to capture the data you need in order to run a computation of a monadic type. This is a question that actually I will formally answer tomorrow. But there is a very close connection. So as I already maybe mentioned on Saturday, maybe it was on Friday. So one difference between the story of interaction laws and handlers is that handling happens always on the computation side. So you have this view that, you know, computations manage on their own. You don't think of them as paired together with an environment and then forming a closed system that can run then according to a fixed interaction law. Rather than in the case of handlers, you work with these ad hoc handlers I'm saying ad hoc not because I despise handlers in any way, but because handlers are never polymorphic. A handler has a specific carrier, so you know how to handle a computation over booleans, or you know how to handle a computation over integers, but you can't ever have a polymorphic handler other than in sort of trivial degenerate situations. But then, and then interaction laws are about talking to the environment, so then the comonads are in the picture. But I know this answer is unsatisfactory. There is more to be said. And I'll really come there tomorrow. But the point is somehow that you can use you can use interaction laws and handlers and co-handlers in combination. And one particular thing you can do is, if you've got an interaction law, which basically says how a monad and the comonad talk to each other, which I haven't got to yet, and if you then also have, for example, have a co-handler given, so if you've got a way to turn any initial state into a whole environment, so evolve an initial state into a process, then that actually canonically gives you a handler for your computations, but not on your original sort of set of values, but rather on functional dependencies of values on states. So it's a handler with a particular carrier, where the carrier is a function space from states to values of interest. But I'll show this sort of technically tomorrow, and that is actually also present in the Haskell code that is shown to you. Maybe we can also discuss this. I wasn't able to attend to the Slack feed yesterday, but I'll go and check a bit now and write some answers to the things that were already there. But yes, I'm sorry this is incremental, but I have to build up a whole lot of little things before we can get to the meat, so to say. And for those of you that know comonads and monads from before, nearly everything I've said so far is trivial, except for a few intuitions and maybe this emphasis between sort of intensional and extensional, like general monads versus free monads, or general comonads versus co-free comonads. But the interaction laws is the entirely new bit, which is different from handlers or co-handlers.